I'll resume and then I'll bring everybody in. Okay, so I will start now. So welcome everybody, good morning, good afternoon, or good evening, wherever you are. So this is the virtual seminar series, and this is the talk in April 2022. So we are IEEE ComSouth Society for TCCN, and this special interest group is AI and machine learning in security. The chair is Professor Subbalakshmi, and she couldn't attend today due to other conflicts, and I'm the vice chair of it. So currently we have about 383 members in LinkedIn, and it is always growing, it is constantly growing. And to join the Security SIG group, you can either go to this particular link, or it is also searchable under IEEE AI and ML and Security Special Interest Group. So if you search, it will show up. And we always post the talks in TCCN mailing list as well. Or you can also send us an email to Professor Subbalakshmi or to me. So we started this talk, we have been doing this talk for a long time. We started this talk in 2020 when we realized that we cannot travel anymore. We are getting fewer face-to-face interaction and all those that we used to do in pre-COVID days. So the inaugural lecture was by Professor Vince Poor in 2020. And then we had a bunch of lectures in 2021.
I mean, it's bigger off order to choose me sometime.
Please mute yourself during the talk. And then in 2021, we had a lot of the speakers. And then in 2022, this is our fourth speaker. So the recorded talks, if we get permission, we have the recorded talks in SIG, which is, this is the special interest group website. They are posted there as well as the slides. They are also available in our YouTube channel. So we have a YouTube channel, and all the talks that we were able to record, they are posted in that channel as well. So let's talk a little bit about the logistics of the talk. Everyone is muted on entry, so please stay muted throughout the talk. And feel free to type in any questions for the, excuse me. Okay. So feel free to type any questions for the speaker in the chat box, and these will be read at the end of the talk. So today's speaker is Professor John M. Shea. He's a professor and associate chair for academics in the Department of Electrical and Computer Engineering at the University of Florida, where he has been on faculty since 1999. His research is in the areas of wireless communications, networking, with emphasis on military communications, software-defined radio, network autonomous systems, and security and privacy in communications. He was a co-leader of Team Gator Wings, the overall winner of the DARPA Spectrum Collaboration Challenge, which is the DARPA's 5th Grand Challenge, in which the teams use software-defined radios to implement intelligent radio networks for collaborative spectrum sharing. He received the Lifetime Achievement Award for Technical Achievement from IEEE MILCOM Military Communications Conference, and is a 2-time winner of the LRSIG Award from the IEEE Communications Society for the best paper in the unclassified program of MILCOM. He has been an editor for IEEE Transactions on Wireless Communications, IEEE Wireless Communications Magazine, IEEE Transactions on Vehicular Technology, He is the author of more than 130 refereed journal and conference papers, as well as 6 book chapters. And with that, I would like to ask Professor John Shea to take the stage and talk about the exciting talk that we are all waiting for to listen.
All right, thank you, Dola. Mostly, did I get the sharing right? It doesn't look right.
Yes.
It's okay. Okay.
That's right.
All right, great. So yeah, I want to talk to you today about some issues relating to AI and privacy in collaborative spectrum sharing. And in particular, I want to try to just give you some ideas about what we have experienced through our participation in the DARPA Spectrum Collaboration Challenge and our research since that time. And let me just start by giving an overall overview of the talk here. And I'll start just by discussing some of the spectrum management challenges, especially those that were trying to be addressed by the SC2, the DARPA Spectrum Collaboration Challenge. Then I'll delve a little bit into the structure of the SC2 and motivate what was going on with that, and talk a little bit about our particular approach in the SC2 in terms of our system architecture. And then I will get into what we were trying to do to adapt, learn and adapt during the competition and after the competition, what we've done in the area of machine learning and spectrum decision engines, some lessons. And then I want to get into some of the research that we've tried to address issues since then, in particular, talking about privacy in collaborative spectrum sensing. And then I'll talk about the next steps, open problems, things like that, that I think the community needs to be addressing, and hopefully we can have some discussion. So we'll start with the first thesis, spectrum management, and in particular, what were the insights from the SC2? And if you don't know about the SC2, it's a big competition run by DARPA from 2016 to 2019 was the core competition. With the goal of using artificial intelligence to unlock the RF spectrum. And so I'll try and give you some ideas about maybe what they intended by when they say, unlocking the RF spectrum. In particular, the SC2 targeted developing distributed and autonomous spectrum management solutions that can respond in real time as users and traffic evolve, and in the presence of incumbents, both active and passive. So for instance, on the top left here, this is a sort of sketch of a scenario that was present in the DARPA Spectrum Challenge called Slice of Life. And during this scenario, what you have in this image is a picture across time. There are 5 different stages, and it illustrates as curves with different colors, the loads that different teams are experiencing across these different stages. And so what you see is during each different stage, a different team will have a very high load and other teams have some fluctuating loads. And so the teams sort of need to adapt to the changing loads that are occurring across time. And they're, the teams just experience these loads as sudden changes in the traffic that they're being given and the priorities that they're being given. That it's not something that you know ahead of time what's going to happen. On the right here, I'm illustrating a scenario with an active incumbent, and the little zoom in box hopefully it'll be visible on your screen. It's a little bit light colored here, a very light radar system that's present. It has about a 1 megahertz bandwidth. And when the radar is present, when this radar turns in the direction of your team, you need to make sure to quiet all communications within the sensing bandwidth of that radar, which is maybe 5 megahertz, and or maybe the whole 10 megahertz, just depends on the particular scenario. And so here you can see, like, to the right, this is a spectrogram showing a typical capture that we got from our radio system. And when the radar is present, we would try and turn on and adapt. And then when the radar turns off, then we can use the spectrum again. On the bottom left is an example that shows sort of a scenario that DARPA envisioned, and we had some experience with passive incumbents such as Earth satellite sensing systems or radio astronomy antennas that can tolerate a certain amount of interference, and then they will provide reports and thresholds of how much interference that they can tolerate. And the teams have to work together to avoid violating the threshold of interference for those systems. So there are different types of incumbents, want to be adaptive to all these things, want to be able to respond. This breakout window that I show here is 100 milliseconds. We want to be able to respond in at most seconds, and sometimes in the presence of incumbents, milliseconds, to adapt to what's going on, not the type of slower changes like one-day changes you see in things like CBRS. We want systems that can respond to very diverse sets of users and applications. So this is just some more spectrograms we captured from a scenario called Alleys of Austin that I'll talk about later. On the left, you see there, I think there's probably 3 teams here, and the traffic is very sparse. You know, it's probably just VoIP, voice over IP, or some command and control types of things like this. On the left, in a later stage, users have all sorts of different traffic, including video flows, files, and all sorts of things. And we want to be adaptive to these changes in real time. And not only that, we want to not necessarily require any specific channelization scheme. We don't want to say everybody has to do LTE. Everybody has to do 5G NR or whatever. Like, users should be flexible, and the system should accommodate different types of channel usage. So greater flexibility, rapid adaptation, diverse user strategies and goals all make coordination of the spectrum very challenging. And so one of the key things that DARPA was pushing in the SC2, and one of the things that we saw, is that the collaboration is one of the keys to enabling us to have this high tempo of adaptation and the flexibility. But for that to work, you have to have some sort of scaffolding to support the information interchange, meaning we have to have some sort of actual channel to exchange information. We have to have protocols, but not only that, we have to have some incentive to have accurate reporting about what teams are doing, what they want to do, what their goals are, location information, and a lot of that's very sensitive, and I want to get into that a little bit later. You need some, a much greater level of intelligence, especially when these decisions are being made in a distributed fashion across different teams or users. And collaboration here, it doesn't mean centralized coordination. We want the decision making to be distributed across the users and have minimal infrastructure. So the idea is there is no SAS, no spectrum access system that's coordinating the spectrum in any area as there is in like a CBRS type system. So what did we observe from the SC2? The key thing that we observed is that I think they demonstrated that it's possible to achieve these types of goals with existing technology. However, there's still a lot of work to be done. So, how do we make these schemes efficient? How do we make these schemes secure, preserve privacy of the users? And how do we incentivize good cooperation, good collaboration? How do we enforce users doing what they say they're doing? And so these are some of the things that we want to get at a little bit later in the talk. So let's just dive in a little bit into the SC2 itself, just so you can have some idea about how we experienced some of these topics. And so here again is the basic top high level scenario for the SC2. So you have, it's a competition. In the competition, you have multiple teams. These teams were from academia, industry, some individuals. Teams were from the US and from around the world. And each team built, whoops, don't want to go ahead yet. Each team built intelligent radio networks that were going to interact with each other in a dynamic spectrum access environment. Up to 5 teams. Each team could have up to 10 radios, and they all occupy the same frequency band. Again, there's no structure to the frequency band or the communication, say, physical layer used by these radios. There is a lightweight collaboration protocol here, the SIL at the top, and a network that allows one radio on each team to sort of communicate with the other radios. Those were called gateway radios, and those gateway radios can kind of coordinate across the teams. Then those teams are given a variety of IP traffic. Let me see how I turn my pointer on here. if I can do that. Yeah, so I'll do this. So teams are given a variety of IP traffic with all sorts of different quality of service requirements. I'll talk more about that later. And then these radios are mapped onto real world scenarios, mobile radio scenarios. And in addition to that, the scenarios can include incumbents, and these incumbents can be other types of non-collaborative radios, including passive and active incumbents, like I mentioned before, but also jammers. And the mobile radio scenarios were emulated using what DARPA calls the world's largest wireless radio emulator, channel emulator. It has 128 different radios in it, and the emulator can allow you to connect up the 2 transmit and 2 receive antennas to all the other 256 transmit and receive antennas in the system. So it's quite large emulator. It's a lot of fun to work with. So in terms of the competition, it is a game. So there's scoring, and that is one thing that is not realistic, but is an enabling technology that allows us to understand how we are performing with other teams. And so understanding something about the types of scoring structures is important to understand how DARPA was pushing us to do different things and the impacts for later work. So each team will score points by delivering some of these different IP traffic flows. All of them have different quality of service mandates, such as throughput, latency, hold times. We have to sustain, continued throughput and latency over certain times. Their deadlines for files, things like that. A team's match score is computed in 2 different ways. If every team is scoring over some specified threshold, then each team gets the score that their flows would achieve. But if any team is below some scoring threshold, then all the teams just get the minimum score. And so this is to incentivize teams to collaborate with each other up to some point, but then to work to do even better above that. And so it's a mixed cooperative and competitive game. And even more than that, in the championship, there were 2 different types of rounds called elimination and final rounds, and those also have conflicting objectives. So in the elimination rounds, the goal was to maximize the cumulative match score over many matches, and that incentivized teams to be more cooperative. But if you made it to the final rounds were to maximize the score in each match, which was to rank as high as possible, which was more competitive. And so actually in the SC2 tournament, we came close to being eliminated several times because we had to optimize with the hope that we would get to the final rounds, which meant that we had to use a more competitive and aggressive strategy to prepare for the final round. So again, there is the SC2 is about adapting your use of spectrum across time, and there is a lot of information, but it is, I would say, rich but incomplete. So first thing is you do not have any information about what other teams are doing directly. You're not able to talk to other teams. Teams are not able to tell you what are their waveforms, what's their physical layer, what sort of protocols, what sort of strategies are they using. You have access to none of that other than through observing the radio spectrum. There is no online scoring information. So DARPA is not telling us as we compete in this competition, here's how you are doing and here's how the other teams are doing. All we know is the scoring information that we generate based on the packets that we deliver. And so we have to guess and track how we are doing. Teams will use the collaboration channel, the SIL, to report things including their frequency use, the radio locations, the performance, their score estimates. And so some of these, DARPA did require some veracity checks on spectral use and scores to make sure that teams were reporting accurately, at least in one scenario. But teams don't have to report their true scores when their scores are above the collaboration threshold. So once you get up to that threshold, scoring threshold, then you can just report the threshold above that. And so again, there's this limit on how much information you have about that. Now, an interesting feature of SC2 is that the incumbents do participate on the collaboration channel and may report things such as their channel usage, their interference that they're receiving, their threshold, their tolerance for interference, and when a threshold has been violated. And when a threshold's violated, nobody scores any points. And you don't score points until you sustain that threshold not being violated for some hold time. In addition to this information that goes over the SIL, then also you have spectrum sensing. You can we looked in the spectrum and use that to estimate what is our peer channel usage, when is there a jammer present, when is there a radar system present. You have to be able to do all of these things in real time as well. And so here is a very simple scenario to give you an idea. The different colors are the traces for different teams as they move through this scenario called Alleys of Austin. These alleys are these urban canyons in the suburbs of Austin, Texas. There are set of ground troops that are moving down these different alleys. And then above, each team has a UAV that circles above. There is also a very fluctuating interference environment as these teams pass across other roads. You experience different levels of interference over time. And so teams seem to be closer or further depending on the particular propagation characteristics that were captured for this scenario. Usually there were up to 5 teams here, sometimes 3 teams sharing 20 megahertz of spectrum. And across multiple stages, you have increasing levels of traffic. So in the first stage, you just have voice over IP and command and control streams. In stage 2, you add on video streams and a file. And then stage 1 has video streams and a file. And then the third stage has even more video streams and more files. And this traffic just goes up and up. And so let me show you a little bit about what this looks like in terms of performance. So I showed you some of these graphs before. And all of these are captures generated from our own tooling that we developed to work on the competition. On the left, you see a score per measurement period. MP is a measurement period across the match time for a match in this particular experiment we conducted. On the right, you see the spectrograms from stage 1 and stage 3 showing, again, at stage 1, teams have very low traffic. In stage 3, teams have a lot of traffic. Then in the, I think somebody's unmuted, please mute. In the graph on the left, you can see the scores increasing as the stages go on. So in the first stage, most teams can achieve all of the goals. In the second stage, then the scores start to differentiate a little bit. Our team, Gator Wings, is the green, so we're doing a little bit better than the other teams that are here. These other teams are Marmot E and Xylenium. This scores were captured during what's called a free play round, where we could compete with 2 anonymous teams that we wouldn't actually know who they are, but we use machine learning to figure out which teams we were competing with in each event. So we could label these as actually being these 2 particular teams. And then stage 3, then you can see very different performance across the teams. And if you can see, there's a light green shading behind here, and it disappears in the third stage sometimes. And whenever the light green shading disappears, that means when the threshold's been violated and the scores are all limited to the minimum of the team's scores. And so some of this, Xylenium is actually one of the best teams in this competition, but teams were playing with their waveforms and strategies all throughout. And so you would see things like this happen, and you can see how busy the RF spectrum is during stage 3 for these teams to try and deliver as much information as possible. But you don't want to have a situation where another team is pushed below the threshold and you all start to score only at the lowest team scores. So let's look at another scenario. So here's one again. I showed you this sort of slice of life scenario where teams have different traffic loads across time. DARPA showed this sort of pie chart here to show, what is the proportion of time being used by different teams, but the pie chart has these different regions that kind of help illustrate that the pie is being used more than 100%. In other words, there's spatial reuse going on in these scenarios. This scenario kind of models like different wireless access points distributed around a, say, urban mall, where different users are affiliating with different access points, and there are different surges at different times of the day at these different access points. And if you look up in the top left of the pie chart, it says 206% total. That means that the amount of spectrum being used at that particular time was 200% of the available spectrum, meaning you got over 100% extra spatial reuse of the channel. In this particular time, Gator Wings is this orange curve, and we were in the surge condition. And so we were able to score a lot more points because we have a lot more traffic during that particular time. And so we were using a lot more spectrum. So probably we are using, more than 50% of the spectrum just for our team, while we have to also make sure that the other teams do not violate their thresholds. Here's a scenario again. I showed you the picture for passive incumbent before the sort of cartoon. Here's what a capture of our bandwidth usage across time. So our bandwidth is shown as the blue line. The dashed black line is the incumbent power report, how much interference that he's receiving. So again, at like a radio astronomy antenna. The red dotted line is the threshold of power interference that incumbent can tolerate. And this is a 5-team scenario. The teams are listed over here, but it might be hard to read them all. And what you see is that as the incumbent power gets closer to this threshold, then we will drop our bandwidth down. So we will use less power by instead of adapting the power in each channel, we'd actually use fewer and fewer channels to try to support some fewer flows that we didn't think we could accommodate anymore. And if the threshold drops too low, in fact, we may have to turn off our transmissions entirely for some period of time, because the threshold will reset if it's not violated for a while. And on the left, you can see 3 stages of this competition, where it starts out and the threshold is actually pretty high and everybody's able to communicate whatever they want. In the second stage, the threshold gets more aggressive, but one of the teams is having some problems delivering data. In the third stage, the threshold's violated, but some of the teams keep transmitting, and we're never able to get the threshold to not be violated, and nobody scores any points in the third stage. And so dealing with these things is challenging, especially in a collaborative environment where you want to score as many points as you can, but it's the combined usage that determines when the threshold is violated. This is another example. Again, I showed you part of this. It's the active incumbent vehicular radar scenario. Here is an example where our team is working well with the other teams. We all turn off and we're able to not violate the incumbent's threshold during this time. The radar signal is able to go through. When it turns off, we all transmit again. On the right-hand side, you'll see a case where some team fails to detect the incumbent and turned off, and the net effect is that we won't be able to score any points for a while after that, because his performance was violated. And here's an example from the jammer scenario. There were different type of jammers, frequency hopping, etc. But this is the simplest one, where you just have a jammer that's on for some sub-band of the total bandwidth. When this occurred, there were teams that had different strategies. Some teams do not have any tolerance for interference, and they all have to flee outside of here. Our strategy was fairly adaptive, so we can transmit in the jammed region if we drop our modulation encoding to lower rates. When the jammer's off, then we can use the entire band. We probably were using some of the band here, but you just can't see it because the jammer is so strong. And to give you an idea, here is, I think there's 4 stages across here with different levels of jamming. In the first stage, there's no jamming. In the second stage, then the jammer comes on. In this curve, Gator Wings is the purple. Xylenium is, again, one of the top competitors, is the gold. And when the jammer comes on, some of the teams have some real disruption and can't get as much data through, can't track where the jammer is, things like that. And so these are some of the challenges you have to be able to handle in real time through sensing and adaptation. The jammer doesn't tell you where he is. So let me just give you a brief overview of our architecture. That was how we tried to address these issues. Overall, our goal was to make our radio stack flexible, agile, robust, make everything adaptive as possible. So lots of different things across the physical layer, link layer, and network layer. In addition, in some of the scenarios, it wasn't always to our advantage to be cooperative. We could be a little competitive and do additional transmissions that might have the effect of jamming other users. So there are lots of different things that could be done, and we tried to do as many of those as we can. Here's the basic overall radio system. The outside looks pretty much like any radio system that you might see, except the way we kind of organized our layer 2 is to split the link layer and MAC, so that the MAC actually releases packets as closest to the transmit system. But the main thing is this decision engine in the middle, which consists of an interference map that we generate by taking in the information provided by the other teams from the SIL, as well as taking in our measurements of the channel, detections of incumbents and jammers. We put all those things into a sort of a map across space and frequencies. The link manager is essentially our control plane. It distributes information about our plans, our sensing, everything across our network. The pocket scheduler, I'll talk about a lot more, is how are we going to use channels across time and frequency. And so that's the overall gist. We did use sort of a LTE type of structure for using the radio resources. So we have time slots and frequency division as well, multiple channels. Radios can transmit on multiple channels at the same time. We call a time frequency block a pocket, just came up, and we have these hot pockets, which are for our control flows and our control plane. And most of our data is ACT data. I won't say too much more about that. I'm just going to jump through most of this, just give you the idea of it. So basically, turbo encoded, QAM modulation with variable QAM, variable rate coding, incremental redundancy, hybrid ARQ. We did have the ability to do frequency domain, equalization, things like that, and receive beamforming as well, because we had multiple receive chains available to us. So I wanted to talk about the decision engines and artificial intelligence. And to give you an idea, basically we want to maximize our team's match score. And the way we do it is we determine which flows are transmitted. So we are provided sometimes hundreds of different flows by DARPA with different quality of service requirements, which channels we use and which radios use those channels for communication, which flows are sent in which particular pockets, and the combined spectrum access action we call the pocket schedule. And so that's really the core of our decision engine. But the action space is really huge. So typically we can have up to 40 orthogonal or disjoint channels, 10 slots in a epoch, so 400 pockets. We can have over 100 flows, as I mentioned. So the number of pocket schedules can be on the order of 100 to the 400, which is some impossible number, more than the number of molecules in the universe, or atoms in the universe, I think even. And we have a lot of information, so a lot of inputs to the decision engine. So we have our own team's quality of service info and performance, all the mandates, all our estimates of the performance of those different ability to achieve those mandates. We have the channel information we measure across the physical layer, link quality measurements. We have SI and Rs from our interference map. We have information from our peers. We can infer who they are again from how they transmit information. We have performance information about how they are doing, where their radios are. Let's see, is that here or somewhere else? Yeah, so their geolocations, their use of spectrum, et cetera. All this stuff is an overwhelming amount of information. And the first thing we kind of realized is you're just not gonna take your average, some neural network and throw it to solve this problem, because the number of inputs are huge. The number of possible solutions are huge. The ability to get training to find any efficient mapping for this thing is going to be extremely challenging. And I'll address that more a little bit later as well. So we use the typical engineering approach of decomposing the problem into smaller pieces. So the pieces we picked are channel selection, determine which channels we're going to actually use. We have both machine learning type of approaches for that, and an approach based on sort of a combination mix of expert system, control, and optimization for that. Admission control, determining, all right, if I know how many channels I'm going to use, I know the number of pockets available, then I know something about signal noise ratios. I can estimate the number of pockets I need to support each flow. I can estimate how many flows I can put in here. I can determine what I should admit to maximize my score given my resources. And basically we use an iterative process to try and maximize that score, just essentially kind of a greedy process for that. And then pocket schedule assignment, where we do the specific mapping of flows to the pockets. And basically it has multiple parts of it. We use a linear program to allocate the proper number of pockets to satisfy latency requirements, because we have flows that have very sensitive latency, have to have this very specific structure. We lay those down, then we use a greedy algorithm to make sure we satisfy the mandates of all the other types of flows. And then we do a mapping onto specific channels based on sort of maximizing the worst case signal interference and noise ratio over the source destination pairs. So I'm just going to talk in detail about one of the algorithms that we worked on recently for determining a number of channels to use. So we have further broke down the problem for one of these. Let's just look at determining how many channels we should use, and the actual channels we can kind of come up with a rule of thumb about, okay, don't interfere with people. Let's avoid causing interference when we don't have to. So this is our ICC paper from 2021, just an experiment sort of trying to look at, can we apply deep Q learning to just essentially discover spatial reuse opportunities automatically. And so we used a 28-dimensional feature vector that includes our own performance information, our score and the threshold for scoring, our current load and our current bandwidth, and then metrics for all the other teams, including their score, their threshold, their load and their bandwidth, and then how much overlap do we have between their signal and our signal, and then what are the distances between the centroid of our network and their network. So this is to help find these sort of spatial reuse opportunities. And so, yeah, we did this as a deep Q learning. The action space is just the number of possible channels we're going to use. Takes in the feature vectors. We used a convolutional neural network with 3 hidden layers. I'll show you the gist of it in a second. And we trained offline, so we would run and collect data in Coliseum. Training online with the batch mechanism Coliseum is not practical. The scenarios are very structured. You have to essentially try something, run it, collect data, then you can deploy again. The loss function accounts for the fact that there's a hold time. You have to hold the time for some capital T time units. And so we need to deal with that when we are updating our Q function. And so I won't go into details of the Q network, but as I said, 3 hidden layers, different widths of the kernels. These are the kernel widths on the bottom. And here are the number of input and outputs between the layers, and tanh activation functions between them. And again, the output is this 21 array vector that then we choose the maximum dose to determine what do we use between 0 and 20 channels. And again, this is Alleys of Austin. So just to remind you what's going on, and the across stages, the traffic increases. And so our performance comparison is if, well, what if we tell the teams they should each use their fair share with 5 teams, 20 channels, each team can use 4 channels. And so the actual channels they use is determined just according to some rough way that we have for disambiguating them, but they are not synchronized in how they determine which channels to use, and they can still change channels if they see an advantage. But generally in the fair share strategy, they will see that it's best to stick to their current channels and not change. Our deep queue network, you see something a little bit different. Each of these colors, again, is for one of the 5 different teams that were present in the network. And when you see a combination that's not present in the legend, like here, then that means that during this time, there are 2 teams that are overlapping and using the spectrum. And what happens is that as the traffic load increases, the teams sort of converge onto a spectrum reuse plan where every team is using 5 channels. And so 2 of the teams, which happen to be the teams that are furthest distributed in space, end up using the channels so they're farthest apart. But earlier on, you see some cases where teams that are not the farthest apart end up using the same channel because they're doing this in a completely distributed and asynchronous fashion, trying to discover how can they find a set of channels that work. You see sometimes that there's empty spectrum as they go through this process. So all of this is done in a distributed and dynamic fashion based on what they're observing and the success of different strategies. And how these teams do this is determined by the queue network, and then our basic strategies for how do we try to choose particular channels. And just to show you that this is effective, if there's only 1 team in the channel, you can score about 26,000 points. If you use a fair share strategy, each team can score about 11,000 points. And the deep queue network is able to score between about 16,000 and 17,000 points by discovering those spatial reuse opportunities, where the only structure we gave it to discover this is that we did provide centroids of the network, so it would know something about how things are distributed in space, but it was able to determine, okay, I should be using more channels and these channels should overlap and with these different teams. So yeah, there's some significant performance in comparison in what we can do by using the SC2 score as our metric. There's still a lot of factors that limit the ability of us to apply deep reinforcement learning. So one we have is that there are only a few scenarios we can use in Coliseum right now, and we don't have access to a lot of different radio designs. We're running against our own team, essentially. So different train networks or the same train network, but different instantiations of the team. The ability to generate training data is really hard. So to generate like a 9-minute scenario takes about a half an hour if there's no queuing in Coliseum. So if your job gets scheduled right away, then for it to boot up all the radios, run the scenario, then move the data back into the public area, and for you to be able to download it and do something with it is half an hour for one scenario run. And so generating lots of different examples is really challenging. And training time and sensitivity to parameter selection are very important. You have to tune all, there's a lot of hyperparameter tuning to make these things work in practice, and then that requires a lot of training time. So try to quickly talk about some of the lessons learned here. One is that we saw that these very diverse intelligent agents can manage spectrum in a distributed and collaborative fashion in timescales of seconds. It really worked in the SC2. We can accommodate all these different types of incumbents, traffic surges, dynamic sharing, etc. And there are two big things. When there's a coordinated objective like we did in the last example, it's a lot easier. And especially again, coordination, exchanging a sufficient information to enable coordination or collaboration is really, really important to this. Another thing that I'll talk less about is, reward structure will drive spectrum sharing behaviors. And that's a real problem for future systems because there's no simple scoring mechanism when you have all these heterogeneous users and heterogeneous systems. The meanings of priorities vary across the applications and the users. I think from my perspective, I think economic approaches can kind of force users to express their priorities in some common terms, which is money. It could be virtual currency if you don't want rich users to grab all the spectrum, but you'll still have all sorts of real issues to deal with, like hoarding, liquidity traps, all these things can cause problems in economic systems. Again, no machine learning black box is going to solve this because of the sizes of the state space, input space. All these things are huge. There's going to have to be some domain specific engineering. Getting training and validation data is a problem. During the SC2, we didn't rely on the ML algorithm or RL algorithm because teams were changing their strategies very rapidly, and we couldn't risk that during the actual competition. So last quick topic is to talk about privacy. I think this is a real big one that's coming up if we want to do these things. In terms of exchanging information, there's a few huge issues. One is you're going to have some mechanism for exchanging that. So the SC2 built that for us with the SIL. We had a protocol, we had a channel for exchanging information. It was very good. But another is privacy. When you exchange information about what you want to do and what you're doing, you can reveal your location if you give people your geolocation directly, or even if you tell people things about what you are sensing in the spectrum, then they can infer where you must be. Your traffic, so if you tell me your QoS requirements, your priorities, your spectrum demands, I can infer what sort of information you may be communicating, and even your device type. So from your traffic types, your spectrum usage, your spectrum efficiency, all these reveal something about your device. So an example of this is we did some work on preserving privacy in distributed spectrum sensing. And the problem we were considering is that we want to exchange our measurements of an RF signal, but if teams have information about different RF measurements of RF signals, then they can infer where the measurer of that signal must be, not where the thing that's being sensed, but where the sensor is. And so our goal is to prevent association of measurement data with a particular radio. And I'm basically going to tell you the three of the approaches we considered and what we actually ended up doing. So one approach is to use fully homomorphic encryption. So we can do computation on encrypted data without decrypting it, but the complexity is just amazingly high. So the only possibility is if you do it with some cloud computing, but even then you're going to have to transmit such a massive amount of encrypted data to make this work. Another possibility is through public key encryption and protocols. So we built a strategy where teams elect a leader and an anonymizer, and all the traffic will be sort of double encrypted and passed through the anonymizer before it's sent to other teams. It has a relatively high communication overhead because of the double encryption. The anonymizer has to use a lot of energy to redistribute all these messages. We built a system that did distributed sensor fusion using particle filtering and showed that we can build a safe mechanism for radios to collaborate with this and achieve something called K anonymity, where they can only pin you down to being one of the K participants. But another emerging way that we recently published about is to use something called secure enclaves. And enclaves are what are known as trusted execution environments. And the idea in a TEE, a trusted execution environment, is the memory inside used by the enclave cannot be accessible from the outside the enclave. And then you can perform private computation inside the enclave at a cost that is orders of magnitude lower than something like homomorphic encryption. And one of the problems is that enclaves can't use a lot of the system level services because those things exist outside the enclave. So those things have to be re-implemented, whatever you need. And one of the nice things about some enclaves is they provide something called attestation, which means that they provide cryptographic evidence that whatever code they say they're running is what you think it is. So it's a way to verify that who you're talking to in terms of a agent is who you think it is. And examples of these secure enclaves are Intel SGX and ARM Trust Zone. So these are being deployed on mobile devices now. And so here are just two different architectures from one of our recent papers at UMCon. On the left, we have a centralized sort of fusion where the sensors communicate directly with an enclave in the fusion center. Again, attestation is used to verify that the enclaves are who they think they are. In a distributed architecture, then again, we have sensors that the enclaves will communicate directly to exchange information. Again, attestation is used. One of the keys here is that private keys that are created in the enclave cannot be accessed outside the enclave. And so we can use public key cryptography to create secure channels between the enclaves, even when those enclaves have to exchange information over to the system services to transmit that information, because it will always be encrypted and only decryptable with the private key that exists inside the enclave. And just to give you an idea about performance results that we saw, so this is sort of a macro benchmark for some of our distributed fusion results, comparing SGX time in running versus just if we run it outside the secure enclave. On SGX, you have some 20 to 40% overhead, perhaps. It's reasonable, I would say, to get this privacy. AMD Trust Zone, we had to implement a lot more of the service type of things inside of there. It has less full support for some of the things we needed to do, and we saw huge multiples in terms of the performance time to run in Trust Zone. So there is still work that has to be done to make these things practical for mobile communication systems. So just big picture, what are our open problems? What are our next steps? We kind of have this vision of a technical ecosystem for dynamic spectrum sharing, building system architectures, developing frameworks to encourage desirable dynamic spectrum sharing behaviors. There's just so many things that have to be done, but some key ones are privacy and security, monitoring and enforcement, making these things efficient, and machine learning could potentially play a big role in all of this. In particular, how do we go about generating, collecting suitable data for machine learning? How can we train multi-agent reinforcement learning agents? In fact, these systems can either be multi-agent reinforcement learning or really stochastic games. All of them have partial observability. So they're really, really hard problems that we don't know a lot about the theory side. How do we ensure the ML solutions are robust to new situations, that this is going to happen? Again, policing for non-compliant abnormal behavior. What role can ML play in preserving privacy? Is there some way that we can utilize the machine learning to compress information that we get the necessary information without exchanging detailed information? And what is the role of machine learning in adapting incentive structures over time to continue to enhance network performance? So I just want to thank all the other people on my team and some supporters. So Tan Wong is really the team leader for Team Gator Wings. He worked on a lot of things. I worked on a lot of system design things and decision engine and coding. Our two PhD students, David Green and Tyler Ward, were the other two primary programmers for the SC2. We had a lot of undergraduate students and MS students that also worked and contributed in lots of different ways. All these people got job offers and are mostly gone. And some acknowledgements of support. So DARPA for running the SC2, developing Coliseum. We had an eager grant that sort of funded our initial work on the SC2. Then all the SC2 prizes kind of helped pay off those countless late nights and supported our students to work on SC2 and continue to support our students. We have the EARS grant for supporting our work on privacy and spectrum sensing and mapping. And then we continue to use Coliseum. It's now at Northeast, so it's a great resource. I would encourage you all to use it. And I would be happy to take any questions that you might have.
Thank you so much. This is a wonderful talk. So let's thank the speaker first. So I don't see any questions. Okay, I do see now. I was going to start my question, but we do have a question from the audience. So this question comes from David Matola. Perhaps I missed this, or maybe it's not relevant, but do receivers employ any interference canceling, for example, for co-channel sharing?
Yes, good question, David. Good to see you. The only thing that we did in our system is we utilized the two channels, the two receive antennas at the radio to do beamforming with the intention of helping to reduce the interference that we were getting from other channels in the system. But yeah, that is a possibility. It's also, to some extent quite challenging because, the interferers can be using any type of signaling scheme in any type of channelization, and the amount of information you have about them is really small. You still can do some interference cancellation in some of those situations, I know, but it definitely have to be, a really blind interference cancellation for sure.
Sure. Okay. Thanks, John. Great talk. So definitely, it's a great talk. I have a few questions, and in between, if you have anyone from the audience, if you have any questions, please feel free to unmute yourself if you want to, because we have a very small group. We can definitely have a conversation, or please feel free to post your questions in the chat as well. So, okay, so this comes from George Scalvantis. Are there scenarios in Colosseum that can be used for emulating directional interference?
So you might want to even unmute and ask this, because what exactly do you mean by directional? Because
Hi, John. Yeah, sure.
Yeah.
Great talk.
Thank you.
I was wondering, I haven't really investigated in detail the architecture of Colosseum, but from my understanding, it's a massive tunnel emulator implemented in the FPGA, right? So how is the modeling of interference is very much different than, I don't know, operating with these radios in an open field setup, right? Where you have omnidirectional interferers with omnidirectional antennas, or you might have interferers that might have phased array antennas and can do beamforming towards your receiver. What were the scenarios, and what are potential future scenarios that could be emulated with the existing setup?
Yeah, so I mean, there is a huge restriction in Coliseum, at least up until it got to Northeastern, is that you have two receive and two transmit antennas. Okay. And I don't believe at that time that the two transmit antennas were I don't know about for sure whether they were synchronized sufficiently to do like what little beamforming, transmit beamforming you could actually do. But within the constraints that you have of two by two, the actual channel emulations they used, I think sometimes they went out and just captured, data for every possible path, like for that Allies of Austin scenario. So you see effects like directionality of interference, in the way that it shows up differently in different, transmit receiver pairs. Those things exist because of the channel, if that makes sense.
Yeah.
But there's very little you can do with 2x2 antennas.
Gotcha. Thank you.
Yeah.
Oh, I thought I saw Francesco here. He might have some more intuition about what's going on now, but I don't see him anymore. Maybe he left. So another thing what I heard for now is we can emulate any kind of channel in MATLAB and download it in Colosseum. Is that correct as well?
I don't know whether that has been implemented. You know, we have been pushing for that for some time because we are very limited. The scenarios are like super complicated in terms of, you know, they have very, you know, they don't have the highest fidelity of channel emulation. They started out having things like frequency selectivity and things like that, so it made it really interesting. Then eventually they sort of went to large scale path loss, but still you had a lot of different, you know, fluctuation over space and time. At least as far as I have used it, I've only been able to use the existing channel models and haven't had, I haven't seen the tool yet that can allow you to implement your own channel model, but that's like going to be a huge thing if we can.
Yes, that's what I've been looking forward to as well.
Yeah.
So let's see. I don't see questions, so please feel free to type in or unmute while I get to ask my question one more time. So you mentioned about the feature selection in the ICC paper, ICC 2021 paper, and you had about like 20 features. Can you talk a little bit about what intuition we should have in terms of feature selection, how much domain knowledge we should bring in to use these feature selection, as well as is more features better or less?
Yeah, and I think this is, you know, when I talked about all the inputs we had for the SC2 and where we're going, you know, we really drilled down to like a small set of features so that we could see what would happen if we, you know, we really tried to figure out what are the core things they're going to affect the performance. You know, this is really a what you call a MARL type of scenario, multi-agent reinforcement learning, where they all have the same objective, because we set the threshold such that they wanted to collaborate and didn't want to outperform each other. So that makes things work a lot better when you don't have like a sort of stochastic game type of different cooperative, competitive type of things. Yeah, choosing the features is going to be really hard in general when you have different types of priorities for different systems. Here, since we were just trying to get everybody to sort of balance the scores was the objective and get the highest minimum score, then exchanging score information and that threshold was important. You know, we thought it was important to sort of exchange information on, you know, what were you being asked to deliver and what bandwidth were you using, but these could be a lot more rich. You know, we could have expected more from the neural network. We could have asked it, said, here are the particular channels I'm using, which channels should I use next time? But just when you do that, the biggest issue for us is that the time it takes for us to collect training data, to have a rich enough body of training data for that neural network to resolve into meaningful outputs, it wouldn't have been possible. So we're really constrained by the fact that every time we run, you know, one strategy, it's like a 30-minute turnaround. We may be able to kick off a few in parallel, but you know, if we're running 5 teams and each team has 10 agents, then we're using 50 of the 128 radios that are on Coliseum already. So that's really the thing that's constraining us. We would like to have a much richer input environment, and so maybe the way to do this is if you have like more flexible scenarios that allow you to run for longer and vary parameters across a single scenario, or keep rerunning the scenario with different parameters. There may be ways to eliminate a lot of the overhead time, because the actual Allies of Austin time is only about nine minutes, I believe. So the 30-minute turnaround to get 9 minutes of data is really harsh in terms of being able to train. So yeah, drilling down to this was mostly a constraint because of the complexity of the network and the amount of training data we would need to resolve to meaningful results.
And that data you bring into the campus and then train everything on campus, I guess. Okay, yeah. Yeah,
that's right. We just, every time a scenario runs, then it'll pull down the data to our local server and then kick off, you know, after we have enough data, we'll kick off a new training run to update all the neural network weights.
Yeah.
But yeah, choosing these things, I mean, it does require domain knowledge. You have to kind of say, like, what are the critical features I'm going to need to have this thing produce meaningful outputs? And so you have things like bandwidth, you have things like scores, but you have things like, okay, well, we think what we're trying to see in this particular instance, we're trying to see whether Q-learning can discover how to do spatial reuse. So we need to tell it the distance is something it should know about.
Right, right.
I had a question.
Yeah, go ahead.
Hi, Dr. Shea. I had actually two core questions. So the first one is about the channel emulation. So beyond 1 terahertz, how well does the channel emulator work? I mean, yeah, I understand that it takes account for large scale threading, but what happens for like a practical scenario, like if there are too much scatterers and everything?
Yeah, so you mean having like a realistic fading, frequency selective fading, all these things?
Yeah, but beyond 1 terahertz. So
Yeah,
like
beyond
how,
1 terahertz.
yeah, how accurately can it do that?
Yeah, I don't think there's any answer about that, you know. So for our scenarios, you know, we're kind of just working at some you can imagine we're kind of working at like an intermediate frequency. So they always just eventually said, all right, you're at 1 gigahertz, and that's where your center frequency is going to be, and then we'll just throw different things at you at that sort of intermediate frequency emulation. I think Coliseum has the potential to do like multipath scattering and Doppler, and all these things are possible in Coliseum. It has a lot of power. You know, the FPGAs inside it are designed to do that. But I don't know, you know, whether there are the tools to build and test those types of scenarios right now. We had some early on in the competition, and I think there were enough problems with just getting the basic Coliseum up and running reliably that they eventually pared those down. And in fact, you saw we built frequency domain equalization, and eventually we just turned that off because it wasn't required in the competition.
Right. Okay.
I think it's also related to the X310. So X310s don't go beyond 6 gigahertz is my guess. So it's the hardware that is causing one of the main problems. So even if we have some simulation or emulation, the hardware is not capable of transmitting beyond certain frequencies.
Yeah, and in fact, you know, Coliseum, its input is a bunch of X310s.
Exactly.
Coliseum itself contains X310s as the input to that FPGA matrix, and so you're going to be limited by whatever daughter boards they've put into X310s there, and so yeah, you're limited to a few gigahertz.
My second question is about the Q-learning paper. So I might have missed this, but does the setup takes in account the temporal variation of channel, or it just assumes that channel stays same over a certain period of time?
Yeah, so it is, we don't have any measures of the say SI&I variations or anything like that in our model. So there is probably the network could be inferring some of that because these loads vary across the stages and some of the interference varies across stages, and it could kind of be discovering some of those features. But yeah, that would be another thing to try, is just over time actually capture some of these, either use more detailed information on signal strengths received on different channels, things like that. It would be interesting to add that as a feature.
Right.
The only way we have it is through the distances. When the centroids change because of the positions of the radios, then that, and then the different loads can also tell the network something about which stage we're in.
I see. Okay. Yeah, that's all the questions I had.
All right, thank you.
Thank you for the talk.
Okay, if anyone from the audience, if you have any questions, please feel free to unmute yourself as well, or write in the chat, that's fine too. Okay, so I have another question. So the question is that you did talk about the privacy of the data, but what about the trust? Meaning that if we have some nodes which are reporting erroneously and some rogue nodes, so how do we work collaboratively in this kind of a scenario?
Yeah, and that's something that happens in SC2, I can tell you, is that we had specific teams that we would flag, that they would tell us their data was something, and we didn't have machine learning telling us that, we didn't have enough time to develop the machine learning to kind of repair whatever they were doing, but we would say, if this report is from this team and it says this below this threshold, then maybe we just ignore that and go on. And so yeah, that having trust that what people report to you is what's really going on is really important. And so I think that is one of the biggest. So some of the biggest barriers I see to implementing this are the privacy that we've worked on. Trust, which I think is terribly difficult because of the fact that to know what somebody's actually doing, you have to try and sense or recover information from them in some way that may be complicated in a rich RF environment. And then the other is just the heterogeneous nature of what flows mean to other people and what their priorities are and things like that. On the trust side, I do think that there may be something that can be done using these secure enclaves that you can require agents to support some sort of secure enclave, and at least use the secure enclave to do reporting. Say I need to have trustworthy information about what channel somebody's using. Mm-hmm. If that's being computed and encrypted within the secure enclave, then I can trust it if I know what that code in the secure enclave is. So attestation becomes a big thing. But if it's being computed just on a regular processor, then people can just make up whatever they want about whatever bandwidth they're using. And so, those problems, if we can make some progress on some of those problems, I think that'll be a really big thing. I think that's, really interesting areas of research.
Sure. Yeah. And so when in the combined usage scenario at the very first, DARPA scores like higher if everybody is doing very well. But if someone is not doing well, or if just one group is not doing well, everybody's score goes down. And how so going one group's throughput going down doesn't really mean that the others are behaving in a rogue manner. It might be because they might not have been capable of transmitting properly. They might have some software glitch or whatever it is, right? So how did DARPA handle that, or it was just as it is?
Well, I think there were some teams that were disqualified at before they got to the final event because they weren't able to,
transmit.
Get whatever they were reporting maybe wasn't accurate enough to meet DARPA's requirements. There was something went on, I vaguely remember. But the main thing was that in all those early rounds of the final challenge, there were lots of different rounds. So you got paired up with lots of different users. And so when you got stuck with some team that was, had poor performance, had a poor physical layer design, couldn't handle interference environments that you see in these sort of situations, they would drag everybody down, but you would get averaged out over lots of different rounds. So hopefully the other teams also have to get stuck with this guy eventually. And yeah, so it is really a big problem, and it'll be a big problem for future systems because you're going to have IoT devices that want to share spectrum with 5G base stations, and what can be delivered between these two things is completely different.
Yeah, absolutely.
but yeah, one of the things is that you have to learn how to work together with all kinds of different teams, and you have to learn to find out what other people can really do and not do. And there's so many different components to a competition like this, from solid radio designs, understanding the problems. Like in the early generations, a lot of people didn't understand that DARPA was just handing us like literally hundreds of flows, and the number of flows that might be supported in the best case might be tens of flows once you get into an interference environment. And they would just pump all the data that DARPA was giving them into their channel, and like, no, flow control, you have to decide, you have to be selective. Things like strategy, again, like the fact that we had to make some tough decisions about how aggressive should our algorithms be going into that championship. The more aggressive we make it, the more risky it is that we won't get into the final round. But if we get in the final round, we have to be super aggressive. So there's a lot of strategization, a lot of fundamentals, a lot of like domain knowledge about how do you make decisions, and it takes a lot of different types of people to make these things work too.
Absolutely, absolutely. Starting from FPGA developers all the way up to the systems and who understands all the realm.
Yeah, I mean, just having like one of our undergraduates, he pretty much just was plumbing together, our backend system with Slack and like pumping data. So like when a job runs, right, makes graphs and pushes them to Slack, and have.
Did we lose you, John? Okay, I think we're back.
Yeah, I had.
Okay, so any more questions from the audience? Okay, I don't see any more questions. I have one last question for you. What do you think it would take to make the DARPA Spectrum Challenge a reality? Like in real life, when do you think and how do you think we can get into a situation where we can use Spectrum collaboratively, and what needs to be done for that? Yeah,
I mean, so there are those three big issues, I think. So the one that you brought up about trust and verification, privacy, and then some mechanism for coordinating across different types of systems, which, like I say, may be economic, I don't know. But I think that there's this new Sci-Nerds call from NSF, which John Chafin is leading, who was involved in SC2. I think he's pushing this thing to keep going, both on the developing systems type prototypes, and looking toward having prototype demonstrations for this in real areas. And so I think it is coming. There's still open research problems and development problems, especially around these topics, and around the role in general of AI and how it can use in these extremely complex environments where it's hard to have enough training data. How do you want something that works on day one when you got there. You don't want something that eventually works 6 months later when it gets enough data. So I think there's a lot of stuff that can still be done, but I think it will come. At least with some spectrum, we'll start to see this, because the potential is so strong because of the bursty nature of data and the non-homogeneous nature of users and their distribution across space.
Sure. Thank you so much. Thank you for talking to us, the group, and letting us know about all the details of the DARPA Spectrum Challenge and how you are moving forward with more work in that direction. And with that, I would like to thank one more time. That would be, if I don't have any more questions. No, I don't. So thank you, John. And
thank you for having me here.
Yep.
I appreciate it.
And we will post the video and the slides after the talk. Thank you. Bye.
Bye-bye.